All right, folks, back here with another video in our study of the derivative, where this time around what we're going to continue with is the development of some of those advanced rules for differentiation. We've talked how to find the derivative for the product of two functions, taking one function, multiplying it by another, and how we have a rule for that derivative for that product of two functions. We've seen a rule for the quotient rule where we have the quotient of two functions, one function being divided by another. And when finding the derivative, we have a rule known as the quotient rule. This time we're going to look at what we can also perform with functions in terms of calculation, and that is composing two functions with one another, right? In algebra, we learned with functions, we can perform an operation known as composition. We can take one function and compose it into another function. We can make the dependent value of one function become the independent value of the other, right? Well, when we consider this case involving two functions, the case for a composition, there is a way to find the derivative for that composition. And the way we use is what's called the chain rule, folks. And let me bring this up. This is our notes. This is what we're going to look at. This is the chain rule of derivatives. Where you can see here we open by just noting, let's consider finding, right? Let's consider finding the derivative of y with respect to x, right? For the statement y equals the quantity x squared minus 4x plus 8 quantity cubed. All right? This is a case where we do have a composition of two functions, right? What we might note, right, is we do have the quadratic function x squared minus 4x plus 8 composed within a cubic function, right? We might consider this is the case that we have for y here, right? We have this composite of two functions. Now we could go about evaluating this, right? Finding the derivative by considering finding the derivative for the expansion of this quadratic, taking x squared minus 4x plus 8 and multiplying by itself 3 times, which would produce a sixth degree polynomial, right? And we could then evaluate the derivative for that sixth degree polynomial. But that expansion could take a few moments. And we could arrive at a solution much quicker than putting ourselves through that expansion. And as I may have noted in other videos too, what we are going to want as we move into some application oftentimes is going to be a factored form of our derivative, which is going to also result more often from a chain rule application than it is from an expansion in this situation. And if we want the derivative of a sixth degree polynomial, well, we know that that's going to be a fifth degree polynomial. And if we have to return that fifth degree polynomial to a factored form, that could be a tricky operation, right? So we do have, as an alternative to expansion and using our fundamental rules on that sixth degree polynomial, what we call the chain rule. Because this is a composition of two functions. Right? Here we're going to assume f and g are two differentiable functions where their composition is also differentiable. And we're going to consider what's the derivative for that composition. Right? Remember, f composed with g at the value of x is when you take g of x and make it the independent variable in f of x. Right? So the derivative of that composition is just the derivative with respect to x for f composed with g of x being f's independent variable. And the result here is stated as we see. It is going to be g prime of x. It is going to be that interior function in the composition, that independent value, g of x, its derivative multiplied by what here is f's derivative recomposed with g at x. Right? What we might throw into this statement here just to make the connection is that this is g prime of x equal to, well, no, sorry, multiplied by what's going to be the composite of f prime with g at the value of x. All right, let me go ahead and group that a little more grand. Right, to highlight that entire calculation is this result we see right here. Right, we are going to have to take g prime of x times what's going to be the composition of f prime with g. Right, that is this result we know as f prime times g of x. And we could include that in our theorem here just to help make that connection. Right? Now this is one variation of the chain rule. What we do see, I follow up with here, is there is another variation to what we just said. This is a little simpler in its notation. And it says if y equals f of u, and u is equal to g of x, right? Then really what we're describing between these two functions is a composite scenario. This u inside f is being summarized by some function of we call g of x. Right? We are describing this composite scenario f composed with g at x when we think about the value of y. Right? Then what is true in this situation is that dy dx, the derivative of y for this equation with respect to x from this equation must be equal to what we see here is the product on the right-hand side between these two individual derivatives. What's going to be the derivative of y, which is expressed as a function of u, dy du, multiplied by the derivative of u, right, which is going to be a function of x. So we want the derivative of u with respect to x. This is a second variation we see for what we call chain rule. Right? One versus the other is personal preference, which case you would prefer using. I will say, however, the first case is a bit more for beginners, where it identifies the parts you need and helps you identify the parts you need for your solution, right? It helps you identify your initial f and g and helps you work through finding g prime and f prime at g. Whereas the second variation is going to become useful, first of all, in a technique we're going to see develop here at the end of our study of derivatives, and that's what's called implicit differentiation. Actually, that's going to be just a topic or two away. We're going to talk a little bit about some implicit derivative methods. And the way we're going to set that up is with a very similar style chain rule in those techniques. And then when you go on to take Calculus 3, and you're introduced to multivariable functions, you're going to be introduced to chain rule for multivariable functions. And it's actually going to be a set of rules where this is going to be the first rule in the set. And at that point, we're going to kind of abandon this format for that chain rule, right, for multivariable functions. So, the second variation is certainly condensed in its format, but is also going to be helpful in becoming familiar with later on in your study. All right, so let's just take note on that. Now let's look back at our example. for our case, where y equals x squared minus 4x plus 8 raised to the third power, if we're interested in the derivative of y with respect to x for that statement, right, then we do have a composite of two functions. We had already highlighted that. G of x, the interior function being x squared minus 4x plus 8. And if we think about it, that is being placed into, I'm trying to highlight it here, seeing if I can. We're taking that function, that quadratic function, and substituting it into f for g, where if we think about f would then be, in a sense, the cube function. X cubed, if we think about x squared minus 4x plus 8 replacing the x in f. So in our setup here, we might identify that that f is the cube function and g of x is the quadratic x squared minus 4x plus 8. We're going to call out f and we're going to call out g as their independent values. Well, sorry, as their individual values. Individual dependent values. Making up this composite. Now we know from the chain rule above, going with this first variation, I'm going to need g prime, I'm going to need the derivative of g, and I'm going to need the derivative of f, but I'm going to need to compose it back with the function g of x, the function I identified as function g. So down here in this setup, might start with finding f prime of x. Well, that's going to be 3x squared. And then if I recompose that with g, that's going to be 3 times that quadratic. X squared minus 4x plus 8, quantity squared. All right. So you can see here, this setup does imply that f prime is 3x squared. So if I recompose inside of f prime the function g of x for x, substituting in that quadratic inside here for x, I can write this as 3 times the quantity x squared minus 4x plus 8. Quantity squared. That is one of the factors involved in the calculation of the chain rule. The other now just being g prime of x. Well, for g of x equal to the quadratic x squared minus 4x plus 8, we know what that simplifies to. Right, we know the derivative of g prime, would be 2x minus 4 from just our fundamental rules. Right, taking the derivative of g prime here. Right, we think this is going to be the derivative with respect to x for x cubed. Whereas this is going to be the derivative with respect to x for that. Do I still have it stored? Yes, that quadratic. And we know from our fundamental rules that, again, this was 3x squared, and this is just the case for 2x minus 4. Right. So the chain rule tells us we're just going to take this result, f prime at g of x, and multiply it by this result, the value of g prime. So thus, from the chain rule, right, we can set up that dy dx is going to be that g prime times f prime at g of x. Or if we bring that into view, we can see that that does give us the quantity 2x minus 4, g prime of x, times f prime evaluated at g of x. Now, rewriting that, right, just dropping the brackets, maybe rearranging it slightly, we can say this is going to be the factored form. And notice this is the factored form. Where does x squared minus 4x plus 8 factor? I don't believe it factors. I think it may not be an irreducible case, but it doesn't factor cleanly. right, into rational zeros. So what is that? Negative 2 and 4, 8 and 1 is not going to get us there. Yeah. So that does not factor. So that is our completely factored form. And we got that nicely from the chain rule. Right? And that is a fifth degree polynomial. If you notice, x squared to squared is x to the fourth times this final x out in front is going to be a fifth degree polynomial. And that is the factored form of that fifth degree polynomial we would obtain initially if we tried expansion. Right? If we would have expanded this value of y. But to having to refactor that, we can see that would be a bit of a tricky aspect of the problem. Right? Now, there was a second variation. Of the chain rule, so we might consider that, right? For this case, where in that second variation, what we want to think about doing is defining y as a function of u and u as a function of x. And in this case, we might let u be the function of x given by the quadratic, x squared minus 4x plus 8, this interior function. We're going to call that out as u. So y then ends up becoming, as we can see here, the value we declare as f of u, which would be u cubed. All right? And what the second variation of the chain rule says, well, dy dx is just going to be the derivative of y with respect to u times the derivative of u with respect to x. So we can set up those derivatives, the derivative of u here, this with respect to x again. Right, is this statement here. The derivative with respect to x for x squared minus 4x plus 8, which equals 2x minus 4. And for this case here, this is the derivative with respect to now u for the quantity of f of u, which would just be the function u cubed. I don't know why I have that in double brackets. Let's clean that up. There we go. We could say it there is the derivative with respect to u for u cubed. And that equals 3u squared. And what the chain rule in this variation says is just the product of these two factors, this times this. All right. But you're going to notice one issue with that when you set that up. So for the second variation, dy dx is just going to be the product of those two factors, which is going to produce this 3u squared minus 2x minus 4. It's going to produce this argument here. Where in this argument here, you can see that involves a u value along with an x value. And that's not what we want. We want dy with respect to x, where originally y was stated for, well, as just a functional relationship with x. There was no u involved. But remember where u came from. Remember, u was the function g of x, this function x squared minus 4x plus 8. So we can come back down here and substitute that in for our value of u. And we end up with, again, the same result we had before with a little rearranging of the factors. 3 times the quantity 2x minus 4 times the quantity x squared minus 4x plus 8, all quantity squared. That's the second variation of that chain rule. This variation, we say dy dx is equal to dy du times du dx. If we can identify how we might express dy in terms of du, which would help us define du in terms of dx, we can just find those individual derivatives of those declared functions and multiply them with respect to each other. And notice, this is what's nice about Leibniz notation. We are looking for dy dx, where we are expressing this in a rational form, which Leibniz did with his derivatives. He expressed them in this rational form. The dy over the dx in general for y equal to f of x. Well, if you notice the ratios on the right, that also express those derivatives now with respect to y and u for the first and u and x in the second, the denominator in the first will cancel with the numerator in the second, leaving you with just the dy over the dx. And we see a rather simplified, well, we see the theory in the formulation. All right. Whereas the first proof, or not proof, first variation of the example here, again, remember, we just declared f and g, the two functions in terms of x that were involved in the composite. We then found f prime and then f prime at g of x and multiplied that by g prime and obtained the same result. Right? The derivative of y with respect to x is equal to the exact same result, folks. So you might want to practice both variations. Right? That's always good practice. But again, there are two variations to chain rule. Right? At the moment, it's preference, but again, I will say this second method is going to become more the dominant calculation. All right, folks, so let's look at some proof. Let me scroll down here to the end. There was our result. If I bring into view, we do have some proof. Why these might get the claim that these are some advanced rules of differentiation might lie in their proof also, folks, because the proof for these advanced rules are a little bit trickier than our other proofs. The other proofs have felt rather intuitive, I think, in their result, at least with respect to the fundamental rules that we saw develop that allow us to find the derivative of a polynomial. All right. But with these advanced proofs, they are a little bit more involved, right? In terms of they have a little trickiness at times, and there are some tricks, right? And I have to show you those and explain some of this away. So the way this begins, right, is we do establish a grand function h of x to be the composite of two others. We call f and g, right, the composite of f and g of x, the two from our definition or the theorem. And when we consider the definition of the definition of the derivative, when we apply that definition to h of x, we get h prime of x, which would be just capital H at x plus h minus capital H at x, all divided by h, where if capital H is this composite, it is looking at f at g at x plus h minus f at g of x, and dividing all that by h. Where to move forward into the next step and develop the results that we have for the chain rule, here's the trick. We are going to multiply this quantity inside the limit, right? If we think about it, we're just going to multiply by the quantity of 1. But we're going to multiply in that quantity of 1 by taking a number and dividing by itself. Taking a quantity and dividing by itself. Where that quantity is going to be a little bit more involved than just the value of n. Right? That quantity, right, that we multiply in, that's the value of 1, is this quantity right here. G of x plus h minus g of x over itself. This is all just the value of 1, if we think about it. Right? So multiplying by 1 does not affect the value of that argument for that limit. It's the same value, but in a different form. To move forward, we now swap our denominators. Since this is a product, we can swap the denominators of these two ratios and have equivalence. So if we swap those denominators, we can actually prepare this statement right here. We're in this statement right here now. We do have two arguments in the grand brackets across this product that involve factors of h. So that limit will distribute itself across these two factors. All right. When it distributes itself, you'll notice what you have actually in the second factor. We'll bring this factor up front with the limit and put its statement right here. And what you will notice is that is the value g prime of x, right, by the definition of a derivative. That is the g prime of x that we multiply by in the result given by the chain rule. What we also have, though, is this other limit for this other factor that we have to handle. And the way we handle that is we go into this denominator here and we declare it to be a value. In fact, we're going to declare it to be the value of n. And by declaring that to be the value of n, you can start to see what happens above is we're going to start to get the definition of the definite integral applied to the limit. Well, applied in the case of a composite of two functions, f and g. Where there's a little bit more involved there, let me show you what we have to do. We're going to let n be equal to g at x plus h minus g of x. We're going to let it be that denominator. Now, that has some implication to it. If we solve that statement for g of x plus h by adding g of x to both sides, that means g at x plus h is just going to be equal to this statement g of x plus n. So this g of x plus h up here in this argument for f can get replaced with g of x plus n. And we should also note as h then heads to 0 in this statement for n, right? As that h heads to 0, this value g at x plus h is going to head to g of x. And if that heads to g of x and we're taking g of x away from that quantity, that value is going to be heading towards the value of 0. So our value of n will also be approaching the value of 0 as h is approaching the value of 0. And we can go swap that out in the argument seen up here, and that's what you see that we do in our next statement. So when we think about h prime of x being g prime times this limit we see above here, right? Swapping out that denominator with the value of n and the quantity g of x plus h with the quantity g of x plus n, we can now form a limit that should be asking about n's behavior, the dependent value of the function as n changes. And here as that h heads to 0, so does n. So we become interested in the limit as n heads to 0 in this argument, where if we spend a moment just inspecting that, what we should see is that is the definition of f prime. If I go back and instead of using g of x, we let g of x equal u, and I substitute out with u there, you can see this is the definition of the derivative being applied to function f at u, which is going to have the result f prime of u, which we could say if we allow u to equal g of x. Right? So it's fair to say that if I replace that u with g of x, and actually I can go back and replace it this way, just by undoing that, right? That similarly, as n heads to 0, for this statement seen here involving now g of x, that is equivalent to what we would say is f prime at g of x. And thus, for the composite of those two functions, f composed with g of x, h prime of x becomes g prime times f prime at g of x. The result that we're familiar with from chain rule. That's the proof, folks. It is a little bit more involved there, a little tricky there. There's some interesting analysis that we have to perform here at the end on this second limit, where it all just follows the definition of the derivative, right? Where we make some changes with respect to what are the variables that are changing in the limit. Right? What this is all description of is chain rule, right? This derivative calculation that we perform when we have a composite of two functions. Right? We can go back to our initial example here, and what we have is the derivative for that composite of two functions. And if we can identify what is the interior function, and we can identify what would be the exterior function, f and g, we can then identify their derivatives and form the parts we would need in the result, the value g prime times f prime evaluated at g of x, what we see in our result down here. Right? We were able to identify those parts and perform our calculation, perform our evaluation. All right? So that's chain rule, folks. That is, again, an advanced calculation of a derivative involving the composite of two functions. There's a lot we can do with functions. If we think back to what we've discussed over the last few lectures here, is at the end of the fundamental rules, we learn that we can take two functions and we can add them together, or we can subtract one from another. Right? And we had the sum and difference rule for derivatives. It was a fundamental rule. The derivative just distributes across the sum or difference. We also note that we can take two functions and we can multiply them by each other. And when we do that, what we're going to have is the product rule play a role. It's going to be the derivative of the first function times the second, plus the first function times the derivative of the second. It's going to develop into product rule, where you can multiply two functions. And then we had quotient rule, which worked not really similarly, but developed in a similar manner, where when you divide by two functions, you can, first of all, you multiply there's a quantity in the numerator that comes from the product of the denominator with the derivative of the numerator minus the numerator times its product with the denominator, all divided by that denominator squared. Right? It's that quotient rule, and it doesn't feel intuitive until you look at the proof. And then the proof provides the proof necessary to accept the rule. And similarly here we have the chain rule. The chain rule, we can take one function and we can take another, and we can make it the independent value into the other function. We can compose them with another. And we know that's going to be the derivative of the interior function, right, times the derivative of the exterior function's derivative, re-evaluated at this old interior. That would be the chain rule. I know I got a little sign language for that, but whatever helps you remember the rules. Product rules, f is the derivative for f and g. F times g is f prime times g plus f times g prime, right? You have to remember your product rule. Quotient rule, right? F divided by g is g times f prime minus f times g prime, all divided by g of x, or g squared. Chain rule. F composed with g is g prime times f prime at g. Right? Chain rule. Right? Those are some advanced rules of derivatives, and you want to become familiar with them. Derivative just doesn't distribute itself in product or quotient rule. And how does it behave over a chain, over a composite? Well, we have chain rule, right? All, again, advanced calculations. But with all that said, I'm done in this video. I will see you in the next one, and I'll see you all in class. So have a good one, folks. See you then.